So now you have seen that the columns of the matrix are important in some sense. So it makes sense to talk about the column space, which is the space that is spanned by the columns of the given matrix A. And that column space is denoted shortly as CS, which stands for column space of A. Now we can easily see that the column space of A is a subspace of Rm, not Rn. This is because A is an m by n matrix, so A only has m rows. So each column of A only has m entries. And so each column of A is a vector in Rm, and if you consider the linear combinations of vectors in Rm, you end up getting something in Rm, not Rn. That's the reason why. Next, theorem 1.8. A linear system Ax equals B has at least a solution if and only if the column of free coefficients on the right hand side is in the column space of the matrix A. All right, in order to prove this, the statement if and only if just means that you will have to prove left implies right and right implies left. That's what it means by if and only if. So now we are going to prove left to right first. Proving left to right means we assume that the linear system has at least a solution. Then we want to show that the B here is in the column space of the matrix A. The linear system or the matrix equation has a solution, at least a solution, which means has a solution. So say that solution is x equals to R1, R2, Rn. This implies the fact that A times this column vector is B. But then matrix vector multiplication is the same as considering the linear combinations of the columns of the matrix, using the entries of the column vector as the scalars. So B is in the span of these column vectors. What is it? It's actually the column space of the matrix A. Conversely, if we know that B is in the column space of A, then that means that B will have to be a linear combination of the columns of A. But this is the same as writing B equal to. Now, this linear combination is in fact the same as multiplying the matrix A with the column vectors S1, S2, Sn. So this implies that x equals to S1, S2, Sn is a solution for the system Ax equals B. And we are done. We have at least one solution, right? Row space, null space, how to find their basis, and the rank nullity theorem. So first, let's discuss about null space. Right. The null space of a matrix denoted as NSA, the N stands for null and the S stands for space, is actually just the set of all solutions of the homogeneous linear system Ax equals 0. A note for you, the null space of A is a subspace of Rn. Why is it a subspace? This is one of the homework assignment question that I assigned to you, proving that the solution set of the homogeneous equation is a subspace of Rn. And why is it Rn, not Rm? Now remember, in order to be able to perform the multiplication of A and X, the number of columns of A will have to be the same as the number of entries on the vector X. And because A has n columns, so the number of entries on the X vector here will have to be n entries. Anything, if it is a solution of this equation, it will have n entries on it. And if it has n entries, it's an element in Rn, not Rn. So we have two special spaces now that we have learned related to a matrix A. One is the column space that sits inside Rm, and now we learn the null space that sits inside Rn. Right. An example, find the null space of the following matrix. In order to find the null space of this matrix, you will have to first consider the homogeneous linear system, Ax equals to 0. But what is Ax? Ax is actually A times the vector column X. How many entries does X has? Well, the number of entry of X will have to be the same as the number of columns that A has. A has 1, 2, 3, 4 columns. That means your X has 4 entries. Right? And you multiply it and you would want to get 0. Now, the next step is that we are going to write the linear system corresponding to the matrix vector multiplication equation here. So you are going to multiply first row with the column here. So that means 1 times x1, 2 times x2, 4 times x3, and 1 times x4. So your first equation will be x1 plus 2x2 plus 4x3 plus x4 equals to 0. Similarly, you multiply the second row with the column vector x here, you are going to get the second equation. And the last row. Next, in order to solve this linear system, you have to set up the augmented matrix. We write down all the coefficients and then add the column 0 to the right. If you pay attention, you will see that when you multiply each row of A with the column vector x1, x2, x3, x4, the first entry on each row will be multiplied with the x1, and so you are going to get the coefficients for x1, that is the first column of the augmented matrix, being exactly the same as the first column of the matrix A. So in practice, you don't have to write a bunch of things like I did here, right? These are useless. You know exactly that the augmented matrix will be just exactly the matrix A with the 0 column added to the right. Right, so if you are going to solve for the null space of A, it's exactly just copying the A. So I'm going to copy the A. And then add the 0 column to the right. And then from the matrix A, you have already set up the augmented matrix for the linear system, the homogeneous linear system. That's very quick, right? Remember, in practice, you don't have to do a bunch of things like I did here. I just did it formally the first time so that you see what is actually going on. Later on, we know exactly the machinery in between them. We can go quick. Our next step will be row reduce it to an echelon form. And again, I prefer the row reduced echelon form. Now from here, you can easily see that your solution is going to be the following one. This is pivot entry. So x1 and x2 are the pivot variables. x3, x4 are the non-pivot variables. Right? And our common practice is to let the non-pivot variable being free and compute a pivot variable based on them. From the equation here, this means x2 plus x3 minus x4 equals to 0. So that means x2 is negative x3 plus x4. And then you have x1 plus 2x3 plus 3x4 equals to 0. Right? So that is going to be negative 2x3 minus 3x4. Now, if you split them into the sum of two columns, one of which is only containing x3 and the other only contains x4, and then pull out x3 and x4 as the scalar multiple, then you'll be able to rewrite this as the linear combination of the column vectors -2, -1, 1, 0, plus x4, 3, 1, 0, 1. All right, so you can see that you have successfully expressed all possible solutions as a linear combinations of the two spanning vectors. All right, so if you call this one capital X1 and this one capital X2, they are the spanning vectors. And the non-pivot variable will serve as the scalar multiple to each vector. All right, pay attention onto the structure of this example because it's going to pave the road to the proof of the next theorem that we are going to discuss. All right, so this means that the solution set, in other words, the null space, is going to be just the span of the vector x1 and the vector capital X2. Right? If you prefer numbers over notations, then you can write this. Either way. All right, so that answers what we need to do for the example, but I want to go a little bit further. If you pay attention, then capital X1 and capital X2 are linearly independent. Why can I say so? Well, if I look at X1 and X2, the X1, the first spanning vector, is actually just setting X3, the first non-pivot variable, to be 1, and the other pivot variable to be 0, and then compute the others by using the formula. Similarly, X2 can be computed by setting the second non-pivot variable as 1 and the other non-pivot variable as 0 and compute the others. Now with the 1, 0, 0, 1 here, if you want to say that X1 and X2 are linearly dependent, then one of them will be a linear combination, in this case, of two vectors. One of them will be a scalar multiple of the others. How can you make the number 1 out of the zeros? It's impossible, right? So there is no way that 1 can be expressed as the combination of the others. And that's the idea. So we see that X1 and X2 are linearly independent, right? Well, you have them being the spanning vectors, which means they form a spanning set for the null space of A. Now they are independent. So this implies that is a basis for the null space of A. So in this case, we can say that the dimension of the null space of A is going to be 2. The dimension of the null space of A is called the nullity of A, denoted as null A. Right, so we can write this as null A. The nullity of A is 2. And the next statement is actually what we have already mentioned here. The spanning vectors are linearly independent. Right. As a direct consequence of theorem 1.12, which says that the spanning vectors are linearly independent, the null space, the nullity is equal to the number of the non-pivot variables of the system. Well, because each spanning vector is corresponding to a non-pivot variable. So the number of vectors that span the null space is going to be the same as the number of the non-pivot variable you have. Now, theorem 1.12. Given a matrix A, the spanning vectors for the solution set of the system span the null space. Well, That's of course for granted because they are the vectors that span the solution set, and the null space is just the solution set. So they are going to be the spanning vector for the null space. The most important thing is they are linearly independent, and that is going to give us a basis. After we solve the system AX equals 0, we have the solution expressed as X equals some number, say R1 capital X1 plus R2 capital X2 plus plus RK capital XK. The X1, X2, XK here are the spanning vector. What are the R1, R2, RK here? Well, they are actually different notations for the non-pivot variable. So this is going to be the first non-pivot variable. You can write it as X3 or you can write it as R1. That's the first, right? So that's why I use R1. Well, your book use other notation that makes it look more familiar, but it's a little bit confusing, right? So because all of the non-pivot variable will have the form x to some index, so they write xi, and because this is the first one, so they add the number 1 underneath the I, and then the second one is going to be xi, and it's the second one, so you add the number 2 below the I, and this is the last one, xik. That's what your book wrote, right? So these are the non-pivot variables. So any xj, where j can be 1, 2, up to k. We don't know how many, so we use k in general, right? Each of them is obtained by setting the corresponding non-pivot variable to be 1 and the other non-pivot variables to be 0, right? That's what we did. So it's obtained by setting the non-pivot variable xij, right? The j is below the I, pay attention, right? Being 1 and the other non-pivot variable being 0. Right? Let me show you what we did in the example so that you can imagine what is going on in the more general setting. You see, this is the third entry, which corresponds to the first non-pivot variable x3. You set it to be 1, the others to be 0. This is the fourth entry, which corresponds to the second pivot variable. You set it to be 1 and the others to be 0. You get the spanning vectors. That's what we do. Then an entry on xj being 1 while the corresponding entries on the other spanning vectors are on 0. So this means xj cannot be a linear combinations of the others because you cannot make 1 out of zeros, right? Right, so any xj, say x1 cannot be expressed as a linear combination of the others. X2 cannot be expressed as the linear combinations of the others. If none of them cannot be expressed as a linear combination of the others, this implies that they are linearly independent. And so we have proved theorem 1.12. All right, so this is the way we are going to find a basis and the nullity or the dimension of the null space of A. The row space of a matrix A, denoted as RS, R stands for row, S stands for space, is just the span of the rows of A. All right, so here's an example, and I would like you to read it. That's on your book, in your book. So two matrices are said to be row equivalent if one can be obtained from the others by applying a series of row operations. Now, proposition: if two matrices are row equivalent, which means you can obtain B from A by a series of row operations. That means the rows of A and the rows of B can be very different. However, the row space, the space that are spanned by their rows, end up being the same. That's surprising, right? Two completely different set of rows or vectors span the same thing. Now, I would like you to read the examples here. The book has done a very good job. You need to utilize it. All right, so here I am going to prove the proposition. If you try to prove it directly, that's going to be very complicated. The other way to prove this is to break it into simpler cases and then combine the simpler cases in a systematic way to get the more complicated case. So proof of the proposition. Case 1. If you exchange two rows only once, so row I exchange with row J only once, right? That means row J of B, that I'm going to use the notation Bj, right? Don't get confused with the notation Bj for the Jth column. We in fact use the same notation for the column and the rows, but in different contexts, in different places, we are going to state it clearly, right? So that means Bj equals Ai and Bi equals Aj. Now you exchange, that's what happened. We need to show the row space of A equals the row space of B. All right. Here, A1, A2, dot, dot, dot. AM, we have M rows, right? Denote the rows of A. And B1, B2, Bm denote the rows of B. So in order to prove the equality here, we need to prove that row space of A is sitting inside row space of B. In other words, being a subset of row space of B. And conversely, row space of B is also inside row space of A. First proof, row space of A is inside row space of B. Well, in order to do so, we start with any arbitrary. We write this to remind ourselves that we are not considering any specific case. We consider all of them at once. Right? For any arbitrary vector A in the row space of A, the vector A can be expressed as the linear combination of the rows of A. Then, because we only switch row I and row J, that means we didn't touch any other rows, so they will stay the same. So A1 is in fact the same as B1, and AM is in fact the same as BM. Now the only difference is going to be at the J and the I position. Because we switch the two rows of A, this means that this is going to become Bj, and this is going to become Bi. All right, and then we rearrange the terms so that it looks normal for the row space of B. Now, whatever we do, this means that we have already successfully expressed vector A as a linear combination of the rows of B. And of course, that means that this guy is in the row space of B. So any elements in the row space of A ends up being in the row space of B. So this means that row space of A sits inside row space of B. Similarly, we can easily prove that row space of B, and this is left for you as an exercise, this sits inside row space of A. So the two implies that they are equal. All right, let's consider case 2. When you obtain B from A by multiply a row of A with a non-zero scalar multiple, and this is applied only once. If you do this, then row I of B, bi, row I of B, is going to be k times row I of A. We first prove row space of A is inside row space of B. Again, the same trick. For any vector A inside row space of A, we will be able to express it as, now because the ith row of B is k times the ith row of A, so the ith row of A is 1 over k times the ith row of B. So we are going to write this as 1 over k, the ith row of B. And because the others, we didn't do anything on the other rows, so they will be just exactly B1 and then Bm, right? But this is the same as writing A as a linear combination of the rows of B. And so this means that you have already successfully proved that the vector A here is in fact in the row space of B. And so this implies that row space of A sits inside row space of B because any elements of row space of A end up being in row space of B. Similarly, if you reverse the process, you are going to be able to write a proper proof for row space of B sits inside row space of A. Now case number 3. What if we obtain B from A by modifying the ith row of A, make it the ith row plus k times the jth row, and this is only once. If we do this, this means that the ith row of B turns out to be the ith row of A plus k times the jth row of A. The other rows of A and the other rows of B are going to be the same. Now from here, we can rewrite the ith row of A as the ith row of B minus k times the jth row of A. But remember that we only made the changes on the ith row. We didn't make any changes on the jth row. So the jth row of A and the jth row of B turns out to be the same. So we can replace it. And this is going to be important later on when I write my proof. First, we'll prove row space of A sits inside row space of B. All right, in order to do that, we'll start with any vector A is arbitrary, right? Not any specific one. Any vector A in the row space of A. We try to show that this vector A is also in the row space of B. Because it is in the row space of A, and row space of A is actually just a span of the rows of A. So this is going to be A1 times the first row of A plus A2 times the second row of A plus dot dot dot. At a certain time, you will hit the ith row of A. So AI times the ith row of A dot dot dot. And at a certain time, you will hit the jth row of A. So that's going to be the AJ, capital AJ. And then you keep moving until you have the last one written down. All right, remember here the index is the m because we have m rows versus n columns, right? So be clear. As said, because we just made changes on the ith row of A, so the other places, the other rows will be the same. So A1 will be the same as B1. AM will be the same as BM. We made changes on ith row by using jth row, but we didn't change jth row. So AJ is the same as BJ. Now here comes this one, where we made changes, right? As explained here, we can rewrite and get AI being expressed as BI minus KBJ plus AI BI. We distribute it. We'll keep this one here, but we are going to combine this one with this one because they have the same vectors BJ here, right? And plus dot 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 plus negative AI times K plus AJ. All being the scalar for BJ. Well, this turns out to be a linear combination of the rows of B, so it is in the row space of B. So we have successfully proven the fact that row space of A sits inside row space of B. Similarly, row space of B sits inside row space of A. This is going to be something for you to do at home, right? All right, so you can conclude that they are the same. All right, so that's very rosy if we only consider one operation at a time, no more, no less, just once. Right. What if we obtain B from A by a series of row operations? That's the last case we need to consider. Well, that means that we are going to apply the first row operations only once to get something, say A1, then we apply another row operation, and then keep moving forward until we get to the B, right? Now, each of the arrow here just means only one row operation. But because we have already proven the equality for case 1, case 2, and case 3, so no matter what we are going to apply here, row space of A will be the same as row space of A1. No matter what we apply here, we'll have row space of A1 equals row space of A2, and so at the end we have they are all equal to each other. So by what we proved in case 1, 2, 3, we know that row space of A is the same as row space of A1, and that is the same as row space of the other one, and that is the same as the row space of the next ones, and that is the same as the row space of the final one. And we are done. Now from the proposition, we can easily prove theorem 2.12. The non-zero rows of any echelon form of a matrix A form a basis for row space of A. So this is going to be a very powerful tool to get the basis of the row space of A, right? So it's important in practice. You are going to use it a lot. All right, so now we are going to prove it. Let's suppose that you have a matrix A, and then you are going to, the best is the row reduced echelon form, RREF, but here any echelon form. By the proposition, we have row space of A equals row space of E because E is obtained from A by a series of row operations. But what is the row space of E? The row space of E is actually the span of the rows of E. Now for the rows of E in any echelon form, you may have a bunch of 0 rows and then non-zero rows, right? So this turns out to be the span of the 0 rows of E and the non-zero rows of E. Now the fact is that the 0 rows of E can be expressed as linear combinations of the non-zero rows. You just multiply 0 to all of the non-zero rows here and you add them together. You of course will get the 0 row, right? if you figure out any rows or any vector that is a linear combination of the other vectors, you can throw them away. We don't need them. After you throw them away, what's left is the span of the non-zero row. So this implies the non-zero rows of E span the row space of A. All right, so next we are going to prove the independence for this to conclude a form a basis for the row space of A. Any echelon form will look something like this. You will have the first non-zero entry on the first row. Now the fact is that the first non-zero entry on the first row can sometimes be not the first entry of the matrix, because you may have a bunch of zeros before that. You may or may not have these zeros, but in general you may have. So let's put them there. Then you have a bunch of numbers that may be zero, maybe not. I use the stars. This is the common practice in linear algebra. And then you search for the next row. Of course, underneath the first non-zero entry, you have to get zero. Otherwise, you cannot say it's echelon. And then you may have a bunch of zeros here until you find the next non-zero entry on the second row. Now, if it were the row reduced echelon form, then this should have been zero, but because we only need echelon form, so here it can be zero, can be not, we don't care, so we write star. And then you may have a bunch of numbers after that. That can be zero, can be not, we do not care, right? Then you move to the next row, right? You search for the first non-zero entry, but before you can see that, this entry is going to be zero because it's right below the first non-zero entry on the previous row. And you will have a bunch of zero until you get the first non-zero entry. Of course, you may have something after that, and maybe more. And again, because this is only echelon form, you do not require the above entries to be zero. They can be non-zero, but we don't care. So we use the star. And you will have a bunch of other rows, right? You will never know how many non-zero rows you're gonna have. So suppose the non-zero rows of E are denoted as E1, E2, dot, 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 and suppose we have K rows, right? Then we consider the dependency equation of this one. Now, when you multiply x1 to E1, that means you are going to multiply x1 to the whole first row here. When you multiply x2 to E2, that means you will have to multiply x2 to the whole second row. When you multiply x3, I don't write here, but when you multiply x3 to E3, you are multiplying x3 to the whole third row. And you keep going until you hit xk. Right? Remember, you are going to add them. What will you have? You will have to multiply x1 with the first non-zero entry, and then add with x2, multiply with the corresponding entry below it, and then add with x3 times the corresponding entry below it, and then do that with xk times the corresponding entry below it. The nice thing is, all of them from 2, 3 up to k here will be all zeros. So you actually just have to care for this one multiplied with x1. Right. To make the notation cleaner, let me go ahead, erase this notation here. The first non-zero entry on each row by something I say E1, E2, and E3, and then EK somewhere. Right, they are the first non-zero entry on each row. So then this vector equation leads to the consideration of solving the following system of linear equations. As I said, x1 times e1 plus x2 times 0 plus x3 times 0. So you literally just have x1 times e1 equals to 0 as your first equation. At the other position, you will have some other equations in the middle here, right? But they are not important. The next important equation you need to care for is this guy. When you multiply x1 with this number, x2 with e2, x3 with 0, and all others with 0. So you literally will have x1 times some number that you don't know, positive, negative, equal 0 or not. You don't need to care for that. Plus x2 times e2. And then because x3 starting from x3, you will multiply with 0. So you don't have to write them here. At the end, you have equal to 0 as the second equation. Now you keep doing that, you are going to get the following. Now from the first equation, because e1 is the first non-zero entry, so it is not 0, you can divide both sides of the equation by e1 and get x1 equals to 0. Once you have x1 equals to 0, you substitute here, you get 0 here. And because e2 is non-zero, so you divide e2 and you will get x2 has to be 0 as well. Once you have x1 and x2 being 0, you substitute to the third equation. That will have you eliminate the first two terms and leaves you with x3, e3 equal to 0. And if you continue doing this practice until the end, you will get all of the x's here to be 0. Well, the only solution you can get for the dependency equation is the trivial solution. That means independence. And that finishes the proof. Right, so next, the definition of the rank of a matrix. The rank of the matrix is actually just the dimension of the row space of the matrix. And because we have already known that the non-zero rows of the echelon form of A will form a basis for the row space of A, that means that the rank will be the same as the number of non-zero rows in any echelon form of A. All right. So you may have different echelon form, but the number of non-zero rows will be the same because they are all the dimension of the row space of A. All right. So here comes an assignment for you. Right. You need to read it and answer yourself. Why should the rank be 3? Next, theorem 2.13. For any matrix A, although the column space of A is spanned by the columns and the row space of A is spanned by the rows, and the number of rows and the number of columns in a matrix can be different. However, it turns out that the dimension of the row space and the dimension of the column space are the same. So surprising, right? So let's first prove it. Now let me remind you a little bit about the pivot columns and the non-pivot columns. If you are given a matrix A that consists of the first column, the second column, up to the last columns, you have n columns here. If you row reduce it to a row reduced echelon form, you'll be able to identify the pivot entries. So you are going to get the pivot columns and the non-pivot columns. Now, theorem 2.2, the pivot columns of A are linearly independent, and the non-pivot columns can be expressed as linear combinations of the pivot columns. Right? Think about the column space of A is the span of the columns of A. But then we will classify the columns of A as the non-pivot columns and the pivot columns. But because the non-pivot columns are expressible as linear combinations of the pivot ones, we can throw these away and reduce our spanning set to only the set of pivot columns of A. Now, because the pivot columns of A is also linearly independent, and because it is spanning the column space of A, it implies that they are a basis for the column space of A. So spanning and independence means basis. That implies that the dimension of the column space of A turns out to be the number of pivot entries on the row reduced echelon form of A. Right? Because each pivot entry will identify one and only one pivot column, so they are one corresponding. But the number of pivot entries on the row reduced echelon form of A is the same as the number of non-zero rows of the row reduced echelon form of A. By theorem 2.12, this is going to be the same as the dimension of the row space of A. This is. Now, as a direct consequence, theorem 2.15 says that if you want to check independence for the rows of A, you only need to get the row reduced echelon form or any echelon form, and then count the number of non-zero rows. Then if you compare and you see that the number of non-zero rows, which is the rank of the matrix, is the same as the number of the rows of A, then it's independent. If it is less, then it is dependent, right? And similarly, if you want to know if the columns of A are linearly independent or not, you just perform the row operations, bring it to row reduced echelon form or just any echelon form. Then you count the number of non-zero rows. That will help you identify the rank of the matrix A. If the number of the non-zero rows, the rank is exactly the number of the columns, that's independence. Otherwise, less than dependence. Right? I will call this part A and this part B. Part B can be proved similarly to part A, and part A is very easy, so I'm going to give you the proof here. First, we are going to prove left to right. So we assume independence for rows of A. We need to show the rank of A is m, the number of rows. The row space of A is spanned by the rows of A. This is obvious, right? Now, if the rows of A are independent, well, you have the spanning and the independent property, so that's of course a basis for the row space of A. But then, because you know it's a basis, you just count the number of vectors in it, and that's the dimension of A. It's going to be the number of vectors in the basis. What is the basis here? It's the rows of A. How many rows does A have? M rows. So the number of vectors is going to be M. And because the dimension of row space of A is just another way to write the rank of A, so rank of A is M. For the backward thing, we assume rank A equals M, and we need to show rows of A are independent. If rank of A is M, remember rank of A is just another way to write the dimension of the row space of A. So that implies the dimension of the row space of A is M. Now consider the rows of A. Note that we have M rows. So that means you consider a set of vectors that has the number of vectors being the same as the dimension. And these vectors are the spanning set for the row space of A by theorem 2.8. That implies immediately that these are independent. And we are done. Part B is similar we are going to use the fact that the dimension of the column space of A is equals to the dimension of the row space of A. This is going to be a short exercise for you. All right, so now let's consider an example to demonstrate the idea. Right, in order to consider if these are independent or dependent, we are going to put them into a matrix. Row reduce that matrix to echelon form and count the number of non-zero rows. Then apply theorem 2.15. If the number of non-zero rows, which is the rank, is the same as the number of rows, we conclude independent. Otherwise, we conclude dependent. Right. So first we identify x1, the matrix x1, the 2 by 2 matrix. Right. Actually, I'm going to stretch it as a row vectors. The semicolons here is to remind myself that it's in fact a 2 by 2 matrix, but I written in another way. But this way is going to be helpful because if you identify x2 as a row vector, it's going to be 1, 0, 1, 0. X3 as a row vector is going to be 1, 1, 1, 1. And x4 as a row vector is going to be 3, 2, 3, negative 1. Now you put them together in a matrix, right? That is the matrix A in our theory, with the rows being these. Then you row reduce it, right, to an echelon. The best thing is the row reduced echelon form, but you can start at any echelon form. And I did it, and it gives me. Right. So then I count the number of non-zero rows. 3 non-zero rows. This implies the fact that if I call this one A, then rank of A is 3. The rank of the matrix is 3, which is less than 4. What is 4? It's the number of rows. Right? So if the rank is not the same as the number of rows, then it's dependent for the rows of A. But look, what are the rows of A? They are these. And these are actually x1, x2, x3, x4 written in another way. So this implies that they are in fact just x1, x2, and x3 in another way of writing. Linearly dependent. All right. Furthermore, we can find a basis for the span of these vectors. Pay attention on this one. So this is going to be equal to. So we want to write 1, 0, 1, 0, but remember this is actually a matrix, right? Then we move to the next one, and remember to rewrite it back to a matrix form. So this is going to be 0, 1, 0, 0. And then the last one, 0, 0, 0, 1. All right, and the dimension is going to be 3 as well. And this is a basis. All right, so that's how we use the theorem. Even if the vectors are not in the row form, we can stretch them and make them being the row. All right, theorem 2.17 can be proven easily. You can read the book, right, and use it. That says the rank of A and the nullity of A, when you sum them up together, is always equal to the number of columns of A.